Hello, welcome to the course SJPHY2C02 Optics, Laser and Electronics. The contents of today's lecture is taken from Electronic Principles by Malvino and Principles of Electronics by V.K. Mehta. We'll continue to discuss topics from Module 2, Electronics. In the previous class, we discussed about the basics of semiconductor physics. So we have seen how a P and N type semiconductor is formed, and we also looked at the evolution of the PN junction diode. So we know that there is an energy difference between the P side and N side. P band is slightly higher in energy compared to N band. So when you join a P type and an N type semiconductor, in between there is a PN junction where a depletion layer is formed, which is devoid of any free charges, and as a result the energy difference between the P and N side increases. In other words, there is an energy hill formed between the P and N side, and the free electrons on the N side do not have sufficient energy to cross this energy hill. So as a result, the current flow or the flow of free charges across the PN junction stops. So if you want to have current across the PN junction, you need to provide additional energy to the free charges. And this process of providing external energy is known as biasing the PN junction. There are two types of biases. One is known as forward bias and the other is known as reverse bias. Let's first talk about forward biasing. So here, the P side of the diode is connected to positive terminal of the battery and N side is connected to negative terminal of the battery. What happens here? So look at the P side. Here majority carriers are positively charged holes, and these positively charged holes are going to be repelled by the positive terminal. In other words, the positive terminal is going to push the holes towards the junction. And on the N side, the majority carriers are free electrons, and the negative terminal is going to push these negatively charged free electrons towards the junction. So the battery pushes both electrons and holes into the junction. Now, in the depletion region, we know that there is a barrier potential. So let's see what happens to the free charges which are getting pushed into the junction. So the free electron, when they try to enter this junction, the pile of negatively charged ions on this side, it is going to push the electrons back into the N side. Similarly, when the holes try to enter the depletion region, the pile of positively charged ions on this side, it's going to push them back into the P side. So there is no flow of free charges across the junction. Now what happens? You slowly increase the forward bias. Suppose initially you have a voltage of plus 0.1 volt. And if this is a silicon diode, the barrier potential is around 0.7 volt. Okay. So you have 0.1 volt trying to move the electron in the forward direction, but you have 0.7 volt trying to push the electron in the reverse direction. So the reverse force is more than the forward force, so there is no current. So you increase the forward bias slightly more, make it 0.2, but it is still less than the barrier potential, 0.3. Finally, you reach 0.7 volt. So you have 0.7 volt pushing the electron in the forward direction, but the barrier potential of 0.7 volt pushes the electron back in the reverse direction. So both these forces cancel. Once again, there is no current. But if you increase the bias slightly higher, you make it 0.8 volt. Now what happens? Your forward bias voltage is higher than the barrier potential, right? So your applied force is greater than the resistive force, right? So here your barrier potential is completely overcome by the applied voltage. As a result, the free charges on either side are able to cross the PN junction. In other words, a tiny current is set up across the PN junction. So when you increase the biasing voltage further and further, the value of the current is going to increase proportionally. So whenever you apply an external biasing voltage greater than the potential barrier, the free charges are able to cross the depletion region and the diode suddenly becomes conductive. So if you look at the barrier potential or the associated field, so you can see that the dotted lines represent the field in the absence of any external field or any external bias. And when you apply a forward bias, what happens? The forward bias is going to act against this external field. As a result, the strength of the external field decreases. When applied voltage equals the barrier potential, these two fields completely cancel each other. Then onwards, you have only the external force acting on the free charges. There are no more barrier field. Okay. Both electrons and holes move across the p-n junction, but for now, let's talk only about the flow of electrons in the circuit. So for ease of analysis, let's look at the flow of a single electron through the circuit. So you have a negative terminal of the battery from which the free electron emerges. It travels through the external circuit and reaches the left end of the diode. It enters the N side. On the N side, the majority carriers are free electrons, so the electron is able to move freely throughout the N region and it finally reaches the p-n junction or the depletion region. As I said, if the battery voltage is greater than the barrier potential, then this free electron will be able to cross the depletion region and enters the p region. Now there is a fundamental difference between electron flow of N side and p side. In N side, this is a free electron. As I said in the previous class, free electron resides in the conduction band. This is a conduction electron. When it reaches the p side, what happens? It sees a hole. Right? Hole is positively charged, so naturally it's going to attract the free electron. But the hole resides in the valence band, whereas the free electron resides in the conduction band. So the electron, which is in the conduction band, comes down to the valence band by losing some energy. Remember, the conduction band is higher in energy compared to valence band. So when an electron jumps down from conduction band to valence band, it loses some energy. So in other words, when a free electron enters from N side to p side, it converts from a conduction electron to a valence electron. So once the electron comes down to valence band, what happens? It sees a positive terminal here. So this positive terminal is going to attract this valence electron. So it continues to move towards the left and finally it reaches the left end. So initially when a free electron comes from N side to p side, it recombines with a hole. So it fills up the vacancy. So in that process, you lose one hole, right? But when this valence electron reaches this end, so it is going to leave this p side. While it leaves, it forms a vacancy here, a positively charged vacancy, which is a hole. So it creates a hole here. So one hole which the p side lost initially, it gains here, so that the total number of holes remains the same. In other words, electrical neutrality is maintained. So once the electron comes out of the p side, it travels to the external circuit and finally enters at the positive terminal. So one complete cycle is formed here. Electron emerging from the negative terminal of the battery and finally reaching the positive terminal of the battery. Okay. Now this process repeats. As soon as this electron reaches the positive terminal, another electron leaves the negative terminal. It reaches the N side. It travels through the N side as a conduction electron, crosses the p-n junction. It becomes a valence electron in the p side, continue to travel towards the left and finally enters the positive terminal. So We discussed about the flow of a single electron, but in reality, you have crores and crores of atoms in your p-n junction diode. So there are billions of electrons taking the same journey simultaneously. So you have a continuous current through the diode during the forward bias. And if you look at the energy diagram, we know that originally there is an energy hill between the p and n side if you do not apply any external bias. So because of this energy hill, the free electrons on the n side were not able to come to the p side. But when you apply a forward bias, it lowers the energy hill. So it pushes the n band upwards so that the energy difference between p and n decreases. So now free electrons have sufficient energy to enter the p side. So once it reaches the p side, the conduction electron loses energy and becomes a valence electron. Normally, in diodes like silicon or germanium, an electron loses energy in the form of heat. But there are special type of diodes known as light emitting diodes, where the electron loses energy in the form of light. So that's the bright light we see from a LED. And the color of the LED can be tuned by controlling the band gap of the material. So typically, when the band gap is higher, it emits radiation in the blue side of the spectrum. And if the band gap is small, it emits light in the red side of the spectrum. Coming to reverse bias, this is a completely opposite story. Here, the p side of the diode is connected to the negative terminal of the battery, and n side is connected to the positive terminal of the battery. Here what happens? The negative terminal is going to attract the positively charged holes towards it. Similarly, the positive terminal is going to attract the negatively charged free electrons on the n side towards it. So as we know, at the p-n junction we have a depletion region which is devoid of any free charges. Now the battery is going to remove the free electrons and holes close to the depletion region. So the width of the depletion region increases when you apply a reverse bias. As the size of the depletion layer increases, the newly created ions in it increases the potential difference or the barrier potential. Now the depletion region is not going to grow infinitely when the barrier potential or the potential difference across the p-n junction equals the applied reverse bias voltage. Then the growth of the depletion region stops. So you can say the width of the depletion region is proportional to the reverse bias voltage. Now, as the width of the depletion region increases, the barrier potential is also going to increase, and as we know, barrier potential is something which resists the flow of free charges across the p-n junction. So since you have a very high barrier potential set up during a reverse bias, there is no current flow through the diode during the reverse bias. And if you look at the energy diagram, the energy difference between the p and n sides increases during the reverse bias. In other words, it increases the height of the energy hill. So you can see from the diagram, the free electrons on the n side do not have sufficient energy to cross this energy hill. So as a result, there is no current due to the majority carriers during the reverse bias. Now, does this mean that there is absolutely no current during reverse bias? No, because so far what we have discussed is the case of majority carriers only. But as we know, in a doped semiconductor, in addition to majority carriers, we also have minority carriers, right? Because majority carriers are provided by the dopant or the impurity, and the minority carriers are provided by the semiconductor atoms. If you provide a thermal energy like room temperature, some amount of electron hole pairs are generated in the semiconductor. The number is very, very less, but still they exist. Now let's see, what does this reverse bias do to the minority carriers. So once again, let's look at the biasing here. The P side is connected to the negative terminal and N side is connected to positive terminal. So in P side, the majority carriers are holes. So holes see a negative potential here, and on the N side, the majority carriers are electrons. They see a positive potential here. Now on the P side, the minority carriers are electrons, right? Electrons see a negative potential here. The negative potential is going to push this electron towards the junction. Similarly, on the N side, the minority carriers are holes. These holes see a positive potential here. So the positive potential is going to push the holes towards the junction. In other words, the applied potential, which acts as a reverse bias for the majority carriers, act as a forward bias for the minority carriers. Right? So the minority carriers are pushed into the PN junction, so you can have a minority carrier current across the PN junction. But unfortunately, most of the minority carriers combine with majority carriers on either end of the junction, because the moment you have a minority carrier electron here, you have a large number of majority carriers holes around it, so the electron is going to recombine with the holes. Similarly, here also the minority carrier hole is going to recombine with the majority carrier electron. So on either end of the depletion region, the moment the minority carriers are generated, they undergo a recombination. But look at the depletion region here. In the depletion region, there are no majority carriers, right? So the minority carriers formed in the depletion region due to thermal energy, they can cross the PN junction and set up a current. Since the number of these minority carriers are very, very small, the current flow due to minority carrier is going to be very, very weak. And the minority carrier current doesn't depend on the reverse bias, it depends only on the thermal energy. That's why the minority carrier current is also known as saturation current. When it comes to reverse bias, there is an important effect known as breakdown. So as I said, in the reverse bias, the energy difference between P and N side increases, so there is no current flow due to majority carriers. You only have a very, very weak current due to minority carriers. So suppose you are increasing the reverse bias. So you start with minus 1 volt, 2 volt, 10 volt, 20 volt, etc. When you reaches a particular voltage known as breakdown voltage, suddenly a large number of minority carriers appear at the depletion region, and you have a huge current because of these minority carriers, and the diode conducts heavily. This is known as avalanche effects. So what happens here? Let's analyze. So when you apply a reverse bias voltage, so this is going to act as a forward bias for the minority carrier. And whenever you put a charged particle in a potential difference, the particle is going to get accelerated. So the reverse bias is going to accelerate the minority carrier. So the accelerated minority carrier moves faster and it collides with a semiconductor atom in the crystal. And if the minority carrier has sufficient energy, it can knock a valence electron out from the semiconductor atom. So suppose you have initially one minority carrier, one electron, it collides with an atom, it knocks out a valence electron, so now you have total 2 electrons. The electron which collided with the atom and the electron which comes out of the atom. So one electron creates 2 electrons. Now these 2 electrons, they get accelerated by the reverse bias, they collide with 2 other atoms and they produce 2 more atoms. So now in total you have 4 electrons. These 4 electrons, they collide with 4 other atoms and they produce 8 electrons. So this keeps repeating. So in every step, the number of minority carriers doubles, right? So this is a geometric progression. So geometrically, the number of minority carriers increases, and within no time, you have a large number of minority carriers in the depletion region. And these minority carriers set up a huge current across the PN junction. So you have a large current flow across the PN junction diode during the breakdown region. And the breakdown voltage is typically high. For a silicon diode, it's around 50 volts. Now some of you may be tempted to think that, okay, originally during the reverse bias the diode doesn't conduct, which is bad, because in any electrical circuit we want the component to conduct electricity. So reverse bias is bad for the diode, but in breakdown you have a large amount of current through the diode, so it is good for us, right? But in reality, breakdown is something which is bad for a diode. Why? Because every material has a finite resistance associated with it. And whenever current flows through a resistive material, inevitably a part of the electrical energy is lost in the form of heat. This is known as Joules heating. This is the working principle behind many of the electrical appliances, like an iron box or a heater coil. So when you have a large amount of minority carriers flowing across the PN junction, a lot of heat energy is suddenly released, and because of this heat energy, your diode gets burned. So whenever you operate a PN junction diode in the reverse bias, you need to make sure that applied voltage is well below the breakdown voltage. Finally, before winding up, let's quickly look at the IV characteristics of a PN junction diode. This is nothing but a graph plotted between applied voltage and the current through the diode. So this is the typical symbol for a PN junction diode. This is the P side and this is the N side. So you construct a circuit and you apply forward and reverse bias voltages across the PN junction. So in this particular circuit, the P side is connected to the positive terminal, N side to the negative terminal. So this is the forward bias. To control the current flow through the diode, you can have an external resistor. Now you vary the voltage and monitor the current through the PN junction diode. So initially, suppose if you're taking a silicon diode, so if your applied voltage is less than 0.7 volt, there is no current flow through the diode. But when it is greater than 0.7 volt, then the barrier potential is completely nullified. So when you increase voltage, you can see there is a proportional increase in current. Okay. And this particular voltage is also known as knee voltage. So above knee voltage, it conducts. Below knee voltage, it doesn't conduct. Similarly, in the reverse region, you connect the P side to the negative terminal and N side to the positive terminal. As we know, the current due to majority carriers is 0, and you have a negligible current due to minority carriers alone. When you reach the breakdown region, you have a large number of minority carriers. So then onwards, for a small increase in voltage, you have a very large increase in current. But you need to completely avoid this region because, as I said, due to high amount of heat energy release, your device is going to get damaged. So this is the IV characteristics of a PN junction diode. So that's for today. I hope that we have discussed in sufficient detail about the working principle and also the formation of a PN junction diode. So with this understanding, in the next class onwards, we can try to analyze some of the important circuits using PN junction diodes. So stay tuned. Thank you.